Good morning, everyone.
Good morning.
How are you? Hi. Do you have any questions about previous lectures? I published also 2 additional assignments.
Yeah.
This hopefully will be not too horrible. And I think this will be the last assignments for this semester. Not trying to load me with more work than you need to have. Previous time that when I taught similar kind of course, it was not really enough for learning dense computations and that kind of stuff. So maybe for next time I will develop some sort of quizzes which are much easier to do, much simpler steps, but more technical, because I think for that kind of course, maybe you still should have some sort of training on doing stuff to understand better like how stuff works. But this is next time, not for this course. So now we will start with all kind of additional topics, which means they're not really, yes.
I think before that, for the line, the code you provided for the image blurring, the taking off regularization. I think that there might be even though the code runs, but I think there may be an error somewhere in the code.
Could be. So what is the error?
So when you invert it, kind of when you're writing the normal equation for the second order regularization, you didn't invert the you didn't bring the inverse for the A transpose A plus the plus lambda I inverse.
Yes.
So you didn't bring the inverse.
Could be. So I need to check that. We'll see. So we practically completed all of the main topics, which are mainstream topics that could be useful for multiple different things. And now I want to talk more about additional topics, which are useful for all kinds of applications and also generic enough to be included in numerical analysis courses in general. So we will talk today about interpolation, extrapolation, which is practically fitting again curves to points, but exactly fitting, not approximately fitting like least squares that we learned already. Sometimes you have that type of constraints where you want your curve or your surface or whatever you are trying to fit, some analytical function to fit particular points. And you want to know what happens between these points and outside of range of this point. So this is interpolation, extrapolation, and I hope also to get, not today, but one of the future lectures, we get also to something which is called particle fitting, which is again very generic approach to solving problems. This is one of the Monte Carlo approaches, which is random sampling type of approaches, which are extremely useful for problems which are not solvable any other way. So we will talk a little bit about that. And then hopefully we'll have another lecture on maybe some neural networks or some other popular thing, which is again universally used in all kinds of applications. So this third part of the course are, I would call it selected topics. And we will see how it goes. They're not really necessary for any application, but they're pretty universal, so you can apply to all kinds of problems. Okay, so today we talk about interpolation and extrapolation. And the basic idea that you want to fit some sort of function, let's call it y of x, and this could be one-dimensional or more-dimensional function, but analytical function, some kind, to pass through n given point. So you have n sample points, which are discrete points, and you try to fit this point some sort of curve or surface, hypersurface. Right? And you have some formula for the hypersurface with particular parameters. So you want to find these parameters for which this curve will pass through all the points that you have, which is not easy task really, if you think about that. Not any curve will pass through all of your points, especially if you have some sort of noise. So with noise, it's practically impossible task to pass through these points. It's something particular, but you have some cases where you can. So we'll call that coordinate x and this coordinate y, so this has nothing to do with vectors x and vectors y. This is just regular XY coordinates, regular Cartesian or rectangular coordinates, and you have some function which is the blue line, which is fitting all of these brown circles. Okay, and each one of the circles we'll call sample point xi, yi. That's yi is 0.5, xi is somewhere between -1 and -0.5. Something like -0.75. Okay, so these are just coordinates of that point. This is just notation so far. All right. We want to calculate values at arbitrary x points. This is a problem of interpolation or extrapolation. So you give me what x you want. It could be, so I have that at that particular point, and I don't have it here. Let's say you want it at that value here. Okay, what happens between these two brown points? So you have only the circles, you don't have the curve. And the question is like, what is the value between the circles? This is what you want to know. So for that, you need to fit some sort of function and compute the value of that function at that particular point. This is what interpolation does. But the thing is that you can fit million of different functions to all of these points, million of different possible curves, right? It's not one possible way to fit given analytical function to a bunch of points. You have infinite number of possibilities here. Is it clear? That you can fit all kinds of curves which are passing through all of these points, but in between the points, they can behave in all kinds of ways. So we are looking for curves which are kind of behaving well or simple in some sense. And these are the types of curves that we'll be looking for. And we will define what it means in particular types of interpolation. You will have particular types of curves, particular types of approaches, how you choose what curve to fit. So interpolation problem is when you want to find values of the function y between the points, which means starting from that brown point to that brown point, from the first point to the last point, somewhere in between, okay, in the range, which is given by these points. Extrapolation is practically the same problem, but you are asking what will happen to that function outside of the range, to the right or to the left, which means somewhere outside of that frame here or there. And practically this is the same problem. Why? Because you fit your function to your points, and you can continue that function forever because it's an analytical function is given by some formula, some kind, right? And if you have that formula, you can compute that formula for any x. It doesn't matter if it is interpolation or extrapolation, so I will not even separate these two problems. It's just problem of fitting the points. Okay? Is it clear how you do extrapolation? You just continue in that line forever. It's infinite range function. Choose infinite range function, like polynomial, for example. And you just compute that value of polynomial at any point you want after you fitted the function. Okay? So extrapolation will be outside of the range of these given points, the sample points. Let's take some simple example. In this simple example, you have some sort of dots, red dots on the plot. So for each value, for 0, 1, 2, 3, 4 sample points, they will have all kinds of values. You want to find that unknown function y, which generated these points in the first place, which passing through all of these points. And these are the values. Okay, these are numerical values of this particular red dots. We have y as a function of x. You want to know what function passes through all of these points. So, when you do that, after you find that kind of approximation of the y function, you can compute for x equals 1.5 as example, or any other value anywhere in space, okay? So 1.5 is not given, we don't know. But what would be the reasonable thing to assume about what happens between these 2 points? What is the value? So it should be maybe somewhere in between them, right? It shouldn't be here, for example, okay? It makes no real sense to put point here, 1.5. Maybe a little bit higher because you have some sort of derivative which is going up, and from that side, it's kind of slopes are kind of going up. So maybe it will be a little bit higher. Also reasonable to assume that you'll have that point somewhere here, closer to 1. Or maybe a little bit below it if it is doing something like that. Okay, before and after. So you can look at the neighborhood somehow, and just by eye you can guess how it's supposed to look like. So this looks more or less like a sinusoidal wave, right? So sine wave would be probably a good thing to try just by looking at the points. But generally, you don't have that kind of guess, right? So generally, you don't know what kind of function you want to fit really, because just bunch of points. Well, how can you guess it? Unless you have some physical modeling or some other modeling and some prior knowledge about the problem, like where it was taken from. And you typically don't have the analytical function. So what you want to do is to approximate it with just basic standard types of interpolation with standard types of functions. The most basic one is practically not even this one. It just holds the previous value. Okay? So you get into a particular point, you hold it at 0 until you get to the next point, then you jump to the next point, you hold it to the next point, which is like flat lines. You're connecting that with steps. Okay, each point connected with steps to the next point until you get to the next point, then you jump to that point, and so on. So this is zero order hold type of approximation. So if you did some electronics or some other stuff in electrical engineering and sampling of signals of that type is called zero order hold. So holding the previous value until you get the next sample. And this is what practically all digital devices typically are doing because they don't know what will be the next point. They sample in particular time in real time. So real-time devices have only information about previous data, so they can approximate, extrapolate to the next point only based on the previous data. And the easiest way to extrapolate in that case, just keep the previously recorded point. This is your value for a while until you get the next measurement. Okay, so this is zero order hold. But this is too primitive for our purposes. So we want some better approximations, especially if you have all these points offline, which means you recorded already all the points. Now you want to interpolate. So you have all the data in the future as well. Okay, so all these points, red points, are available. So linear interpolation is the easiest one, which is first order approximation. Zero order hold is zeros order approximation, just constants. This one is linear. You're just connecting the dots with straight segments. That's it, that's what you do. All right. In that case, let's say y equals to that number and y2, which is that point equals to that number, you would guess y at 1.5, which is in between. It's just average of these two numbers. All right, this is the easiest and simplest way to approximate what should be that value. But I mean, you're looking maybe for a better way to approximate functions because it looks kind of not very differentiable. Let's say, okay, so linear interpolation is not differentiable typically because you have breaking points at these red dots. So you want something more smooth, something which looks more smooth. All right, so here's the formula how you compute these linear segments. This is just fitting line to 2 points. Remember the formula to fit lines to 2 points? Like you give coordinates of xy here and xy here, so you can find what straight line passes through these 2 points. So you'll have practically 2 numbers out of it, which is intercept and slope, right? So slope will be given by this one divided by this one. It's like delta y divided by delta x. This will be your slope for any derivative. It's practically derivative, but in a sense, for straight line, it will be derivative. Okay. So this one divided by this one is slope times x minus xa equals y minus ya. This is how you find formula for the straight line passing through 2 given points. And the points are xa, ya, and xb, yb. Okay, so these 2 points are given to you. Remember from analytical geometry, probably school, somewhere. I don't know where you learn that kind of stuff, but university already. But this is just formula for line passing through 2 points. Okay, if you don't remember it, try to brush it up. All right, so for each pair of points, you put in that segment between them, and this will be the formula for that segment. For the next segment, you take in these 2 points consecutively, and finding that segment. And these 2 points, finding that segment, and so on, connecting them in all these intervals, you get linear approximation. Any questions on that? All right. Next step is to do something smoother than that, polynomial approximation. Now, polynomials of degree n have n plus 1 coefficients. Remember that? Quadratic polynomial has 3 coefficients. Cubic polynomial has 4 coefficients, and so on. All right? Which means that the degrees of freedom that you have in n's degree polynomial is n plus 1, always. You can always fit polynomial of order n to n plus 1 points. This is the overall idea. So given n points, you can pass polynomial of n's minus 1 order to these points, because you have all of these equations. So let's say this polynomial of 6th order is fitted to 1, 2, 3, 4, 5, 6, 7 red points. Okay? And it looks like a sign, but it's not. It's polynomial, actually. Okay? Which is passing through all of these points exactly for these particular coefficients. So the question becomes like, how do I compute these coefficients? How do you know what these numbers are? Okay? But given these coefficients, you can easily compute this polynomial at any point for any x. So for x equals 1.5, you just put x equals to 1.5 to all of these x's here, and you compute the value, which will be 0.98, which is a little bit higher than this one, right? So it's closer to 1, so it goes up here. It will be here somewhere. All right, so far? So this makes more sense for that particular example, okay, where it's kind of going a little bit over and not just connecting these two dots. And now you can, as I said, connect any n plus 1 points with polynomial of degree n. So how do you do that? This is our first failing attempt, okay? Not really failing, it depends. If polynomial of low order, low degree, this would work. Or maybe not, it depends on the points. But in some other cases, it might fail. And the approach is straightforward, okay? So for each point I, so pick any point I, you will have yi by definition equal to that polynomial at the point xi, because this needs to solve it exactly, okay? And I equals 1, 2, 3, 4, 5, whatever, through n plus 1. You have n plus 1 points, okay? So you have n variables, an minus 1 through a0. These are n plus 1 unknowns that you want to solve for. And you have n plus 1 equations. Sounds like a solvable problem. You have n plus 1 equations, n plus 1 variables. All of these equations are linear. Why? Because this is part of vector B, right? And these are coefficients in the matrix A. Okay, multiplying this, no, not matrix A, actually, these are coefficients in matrix X. Okay, so this is column vector X, all of these coefficients an and so on, and these are values in the matrix A, because these are numbers. It doesn't matter if I take them in particular degree or anything like that, it's just still number. It's dot xi, it will be 5, or whatever it is, okay? So here is how these equations look like in matrix form. So you have 1 times a0, which is that thing, plus x1 times a1, which is that thing, plus so on, until you get to an times x1, and this is for the first point, and this will be equal to the value of the first point, which is the value of that function at the first point for coordinates x1 and y1. And then I can repeat it n plus 1 times. Okay, so far? For each point, I'm just repeating single line, single row of that equation. So I get new equation. So I have n plus 1 equations, n plus 1 variables from a0 to an. All I need to do is to invert that matrix, to multiply by that vector of y's, which are coordinates of these points, and I get all of my coefficients out of that. Do you remember what that matrix is? In that matrix before. Name associated with it. Old matrix, before matrices were invented in general, before linear algebra was invented. This is Van der Monde matrix, B matrix, okay? So you saw that when we talked about, we talked not specifically about square matrix, this one is square, but we talked about rectangular Van der Monde matrices, which are more generic. Okay, this particular kind of van der Monde. So here is a problem with van der Monde, okay, in general. This is ill-defined, ill-conditioned problem in math, okay? It's near non-invertible. It is invertible, so you actually can try to invert it. And for small degrees, it will give you correct results. If you try it for higher order polynomials, it will not be good, right? You will get some numbers which have nothing to do with reality, okay? They will not fit well. So what do? We need still to solve the problem, how we pass polynomials through n given points. That all of them will somehow fit the curve. It's like a difficult problem. Have Lagrange to help us with that type of thing. We have Lagrange polynomials, and Lagrange is a very famous mathematician, French mathematician who probably heard a lot about in calculus maybe. Lagrange theorems, like averages, integrals, and he known for multiple other things in analytical mechanics. This is his development. He developed analytical mechanics, Lagrangian, and Lagrange multipliers, and many other things in optimization. So he is pretty known for multiple different things, and he has multiple different things called on his name, right? So this is Lagrange polynomials. And they are very special polynomials, very interesting polynomials, which have very interesting property. Very simple ones, not too complicated. And we'll see what we can do with these polynomials. So the idea is that inverting that van der Monde matrix is completely equivalent to solving the things, okay, using particular polynomials. And I will explain what these polynomials are, but representing your y of x, and this is already representation as a function of polynomials because each one of them will be polynomial times constant. So yj are points that you have, right? Xj are points, the coordinates of the x-axis points. And this is polynomial in terms of xi and xj, all right? So we'll have all of this will be numbers, this will be number, but this is not numbers, this is just variable x. So if you take in that multiplication here, this will be just a number, right? This will be product of all kind of numbers, so it will be a number. And this will be x minus some number divided by some number, which is polynomial, right? It's factorized polynomial already. It will be x minus something times some constant, which is factoring polynomial, right? So that Lj will be polynomial times some constant. And you will have sum of polynomials weighted with these constants, right? Which is again polynomial. So if you're adding polynomials, right, you still get polynomial. Doesn't matter what degree you use. Is that clear so far? So this thing will be polynomial. This is what is important to get from the particular formula. So y of x will be represented by polynomial. And now this polynomial, which is Lagrange polynomial, will have very special properties. And this is a property. So Lj of x will have the following property. At point xi, which is that particular given point, right, that red dot, it will be equal to delta of Kronecker. Delta of Kronecker is 1 and I equals to j and 0 otherwise. So it's almost always 0 for all of these points except when I equals to j. So Lj xj will be 1. But for any other point, red point, it will be always 0. So we build that polynomial in such a way that this will be the case. All right? So let's see how we get there. Okay, like how do you know that this property actually holds? And this is a derivation of Lagrange polynomials, the idea like why this works, why this is the same thing. It's like almost like index polynomial, okay? If it's 1, when you have particular point and 0 otherwise. Everywhere else, but not between the points. So between the points, you will have some sort of values, whatever they are, okay? But at the given sample points, you'll have everywhere 0, except chosen point, where it will be 1. And between the points, it will be all kind of values. This is the idea of that Lagrange polynomial. This is the property of the Lagrange polynomial. So here is how you do that. So given some function y of x, which will be some given general polynomial, an x n plus an minus 1 x n minus 1 dot a1 x plus a0. This is just generic polynomial. And you have n plus 1 points. And these points will be xi, yi. Right? So this is what given to us, sample points from that polynomial. This is what we know. That if you put here I and here I, this will work somehow. Okay, for these points, and we don't know what happens between the points. We want to find out what that is. So we will define that kind of Lagrange polynomial of x. So this is definition. We will have alpha j, which is some given constant to be determined. We don't know it yet, some constant, times x minus x1, x minus x2, and so on until you get to j minus 1. And then you skip 1, j, and then you continue on. You will get x minus xn plus 1. Okay? So practically this is factorization for all of the points that you have except one, which will be point xj. Okay, so skipping that xj here and jumping from j minus 1 to j plus 1. Practically not using that in that factorization. All right? Any questions so far? This is how you define that polynomial. And clearly this is polynomial, right? No questions about why this is polynomial. It's just factored x times another factor, so on. Yes.
The last one is x minus x
N
plus
n plus 1.
n plus 1.
You have total n plus 1 points. This is the last point. You're taking all of the points except the point j and multiplying by some constant, whatever the constant is. All right so far?
Is that x minus xj equals to 1?
Sorry?
X minus x.
X minus xj minus 1 index.
No, x minus xj.
You're skipping that one.
Is that
You're skipping that one. You're not using that one. You're throwing it out from the polynomial. You're not using that to define the polynomial. So you're skipping one point. You're using all points except one. This point is point xj, right? So you can write that also as product of alpha I, j actually, not I. Product where I equals 1 and I not equal to j, n plus 1. Here we'll have x minus xi. Shortcut notation for the same thing. I'm taking coefficient times product from 1 to n plus 1, except I equal to j, all of the factors. Okay, so far? All right. So let's see what happens for that particular polynomial. If x equals to xi, what happens? And I not equal to j. What happens? If this is the case. What happens to the polynomial? So if x equals to xi here, so I have xi, 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 and so on. Not equal to xj. I not equal to j. will be always zero. Why? Because at least one of these factors will be zero. If you multiply zero by whatever, it still will be zero. Right? So L K xi will be equal to zero by definition of the polynomial, regardless of what alpha is or any other factor is. So one of these factors will be zero, multiply zero by whatever, you get zero. Okay? Now, if x equals fj, now I equals to j, what will be that? Lj? 1? No. Only 1. Why should be 1? It will be alpha j times product of all the things. My j will be replacing here the thing. X will be equal to xj. Okay, so I'm just copying that thing where x is xj, that value of the polynomial. Okay, so we have xj minus xi for all the I not equal to j. Okay, so far? Copying the formula. Because it will be all of these terms, whatever they are, multiplied for x equal xi, and xi will be xj, right? In that case, so it will be xj minus 1, xj minus x2, xj minus xj minus 1, and so on. Okay, I'm just substituting xj instead of x. And I get that thing. Now, I want to find that thing such that that thing will be 1, because I want that index type of property. So from here, I will define alpha I, alpha j in that case, to be 1 divided by that thing, which is product 1 I equals 1 not equal to j, xj minus xi. Because I could choose whatever alpha I want. So I will choose that kind of alpha. Given that definition, practically Lj will be that formula, which is product I equals from 1 to n plus 1, I equal to j, x minus xi, and divided by product, which looks very similar, but a little bit different. So what happens is I'm just copying that thing here, which is that alpha, 1 divided by that thing is alpha, times whatever I have there. This is how it was defined in the slide. Right, this is where it is coming from. And by definition, as we've seen, that's it. So this polynomial will be equal to 0 for any point which is not equal to j, I not equal to j. And by definition, as we defined alpha in such a way, that will be always 1 when it is equal, I equals to j. All right? So this is the overall idea. And now, y practically will be linear combination of this function, so it will be something like that. Let's use that space. So y of x will be linear combination, which is sigma j equals from 1 to n plus 1 on yj L j of x. If you write it explicitly, it will be y I at a particular point, x I y, right? At given particular point, it will be that linear combination y1 L1 xi plus y2 L2 xi and so on until you get plus yi Li I so on, and you can continue to the last term, which will be yn plus 1, practically opening that sum, okay? L n plus 1 xi. So pay attention what happens here. So this was the definition of how I defined y of x, again in the slide. Now, if I substitute here xi, particular given point, any of them, okay? Here's what happens. I'm writing that polynomial explicitly. This will be y1, L1 at that point, y2, L2 at that point, plus, and so on until you get to point I. So it will be yi, Li at that point, xi, plus all kind of other things. So if this one is not equal to I, this is just 0, okay? This one is 0. All of them are 0. So all of them disappear completely. They do not participate in that sum. The only thing which is left is that term. And for that term, this thing will be 1. Okay, by definition of Lagrange formula, okay? So this value at xi will be equal yi times 1. This is exactly what you want. So this by definition solves your problem, okay, by definition of the polynomial. Because all of these parts will be 0, this part will be 1 times your value at that point xi that you wanted in the first place. And this will be true for any I, right? So it's like not I specific. For any I, if you put here xi, you will get yi. And this is the coordinate of that point. What it will be in between, it will be that thing, whatever that thing is, and could be some sort of curve, okay? But this curve will pass through all of these points, right? Any questions? Okay. Then you can validate. Hopefully I didn't make any mistake in copying formulas. So this should be the same formulas that we developed on the board. Okay, these two formulas. So y is defined at the right bottom. Lagrange polynomial is defined somewhere in the middle, the bottom part. Right so far? Yes.
Is this kind of a generalized approach of finding solutions for air conditions, linear equation, or specifically?
It's really specific for that problem. Again, I mentioned previous times that we will see some analytical solutions for inverting matrices in a sense. You're not really inverting matrix. You're finding an alternative solution which is analytical, which is clearly analytical solution. So you're finding the actual analytical polynomial which is fitting all these points exactly. And you're not going through inverting the matrix. So you're not dealing with the problems of invertibility in general.
Okay.
You're just solving it in a different way. But solutions are equivalent. So if you will go back to that matrix and you will substitute the given numbers here, and that matrix will multiply these numbers, you'll get correct y values. Okay, so this solves that system of equations correctly. But if you will try to invert that matrix and then to multiply by that vector, you might get different vector here because condition number is horrible. This is a problem. Numerically, it's not stable. I mean, if you're using, so there was question about, like, can you make invertibility a little bit better using numerical methods, just in general? So, and I said, like, yes, it depends. Yes and no. Sometimes you can, sometimes you can. It depends. So people are using, for example, like LU decomposition, QR decomposition, other things, or SVD decomposition to invert matrices more precisely because there you have less numerical errors after you do that type of decomposition. So this is the most generic way of inverting matrices with with high condition number. Okay, you're just doing, for example, SVD, something that we did before, and you're doing that Tikhonov regularization on that matrix, okay, and then it will be more reliably inverted. Okay, this is the way. Is it promised that this will always work? Not really, okay? Sometimes it could work. It definitely works better than just trying to invert it as is, okay? Because you will have horrible values, especially for higher degree. But Tikhonov works much better on inverting that type of matrices. But in other cases, it might fail as well. It's not really promised. It's not proven method for inverting matrices which always works. There's no such thing. At least again, to the best of my knowledge. And I'm not a mathematician who is doing research in that area, so I don't know, maybe people invented all kind of stuff since then, since I looked last like 20 years ago. Okay. So, interesting property of that polynomial, that this polynomial is unique. Means this is the only polynomial which is passing through all of these n+1 points. And the idea is that since this van der Monde matrix is invertible, it has to have only single possible unique solution. Okay? And again, numerically, when you invert it, you'll get wrong solution. But there is solution, okay? We know that there is solution, correct solution. And this is solution given by that Lagrange polynomial and not by inverting the matrix. But solution is unique, which means you don't have any other polynomial which is passing through same points of the same order. You can have higher order polynomials, but not of the same order. Any questions on that? Okay, example, how you apply that. Let's say you have model function, which is branch function 1 divided by 1 plus 25x squared. If you want to imagine how it looks like, almost like Gaussian, bell-like shape, that type of function, bell curve. Not exactly, but close enough, all right? And it is sampled at particular intervals, every 0.2, from -1 to +1. And you have all of the sampled points, right? So I'm taking x here from -1 to +1, sample it at particular intervals, and I'm not telling you what that function is, but you want just to find back some sort of interpolation out of that function using Lagrange polynomials. And you want also to find what is the value of that function at 0.7, which is not given in the table, somewhere between the points. Okay, somewhere here between 0.6 and 0.8. So you do all of that computation of that polynomial, and this polynomial will be, again, sigma from 1 to n+1. This is what we have on the board. Yj times Lagrange polynomial, which is Lj. Okay, this product is Lj. And I'm substituting just x equals to 0.7 here, okay? In all of the things, you get all kind of long computation. Computers doing that much more efficiently, obviously. Okay, but by hand, it's kind of tricky. It's long thing, and you have how many points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Allowances like tens of their polynomials. You have long way to go to write all the things. So I'm not doing that. But the result, if you just use computer and compute all these things, will be -0.226. Does it make sense? Like, look, all these numbers are positive. All of them. Not even single negative number anywhere. The result between these two numbers drops negative 0.6, which is very interesting thing about Lagrange polynomials. So they will cross through all these points. If you substitute instead of 0.7, you substitute 0.8, you will get that number exactly. If you substitute 0.6, you will get that number exactly. But between these numbers, you get negative 0.22, 23, right? Here's how it looks like. This is the fitting. These are the points. Black dots are the points sampled at 0.2. And the black line is the Lagrange polynomial, which is passing through all of these points, for sure. And the dotted line is the original range function. Okay, so this is how it's supposed to look like, that thing, bell-like shape, right? And this is how Lagrange polynomial looks like. So you need to be very careful with fitting and believing interpolations from Lagrange polynomials, because it's that way, okay? So you can have like horrible things between the points using that single polynomial compared to what happens at the points, which is precisely computed, all right? And also for Lagrange polynomials, the worst thing that you can do is even sampling. Like if your sampling is even, like points are equally distant from each other, it's horrible typically. It's not great for Lagrange approximations. You want to sample more at the ends, okay, of the interval, which means more points sampled here in these intervals, where you have biggest change, biggest jump in the things. And here's just one example how you can do exactly the same number of points, but you're picking them like more points on that side, less points in the middle, and more points on that side, like closer to the boundaries, you pick more sampled points. And then it's still not perfect, but at least it's much closer to the original function, okay? And the original function is definitely not polynomial, right? It's rational function. So you cannot expect it to fit exactly the function. You will not get that shape, the like shape from that polynomial, never, no matter how many points you sample, okay? But this is clearly much closer to the original function, okay? If you sample more at the ends. So this brings, yes.
So first you can try like using the same frequency of sample like previous one.
Mhm.
0.2, 0.2,
Yeah.
and find out that we'll get a spike in the
Yes.
in the
And
at the
the
end.
derivative at particular
And then
points,
you-
yes.
Then you change the sampling frequency to
Now, frequency will not help you. Even if you have million points equally spaced and you're trying to pass through all of these equally spaced points, it still will do some completely crazy stuff between the points. You'll have very high order polynomial, which is jumping all over the place. It will be huge variability between the points. What you want is to have less points in the middle and more points at the ends. And it works better. Okay?
so until you first see that there will be some spikes, some unwanted
You-
curve, then you change
I
the
mean, we know that you will have spikes if you're sampling at equal rate. You don't need to look at it, it's just known.
okay,
It
so
always will happen.
always happen in the end.
At the ends, you will have less smooth approximation, less approximation that makes less sense, especially if your original function is smooth and not changing like that, like crazy at the boundaries. So we know that this is just not good approximator for that type of functions, period. So it solves the problem, but the solution is not super great, and this is why people thought about other kind of interpolation. People use Lagrange interpolators in relatively rare cases. This is just interesting theoretically, but practically Lagrange polynomials are used in very limited circumstances. And this is what people typically use. People use spline interpolation, and spline idea is very similar, but each interval will have its own polynomial of particular order, which means between each pair of points, you'll have polynomial of second order or cubic polynomial or something like that. Low order polynomial, which approximates the curve between the points, and then you have completely different same order polynomial between the next pair of points, and so on. So each interval will be practically connected. But then you have a lot of variables and not enough equations. You have infinite number of solutions, obviously, for that type of problem, right? Because let's say you're trying to fit here quadratic polynomial. Quadratic polynomial has three numbers, three coefficients, okay? But you have only 2 points. So you have like degrees of freedom which you're not even using. You can have like million of different parabolas fitted between these 2 points, okay? You can fit only one straight line, but infinite number of parabolas. You can different segments of parabolas. It can go like that, it could go almost like straight line, it could go all kind of ways, okay? So what do you do with that? So you need additional constraints. And this is what spline interpolation is doing. They are trying to do it in such a way that connections from here to there will be smooth, like before the point and after the point. What does it mean connection is smooth? Derivatives will match. So the derivative on that side, on the left side from the point, will be equal to derivative on the right side. And you can think about first derivative, second derivative, as many derivatives as you want, okay? Depends on the order of your approximation. So if you're using, for example, quadratic polynomials, you can use first derivative, cubic polynomials, like 2 derivatives, and so on, to give you additional constraints, which means that whatever comes from that side should continue exactly the same slope, tangential line, and derivative of tangential line on the other side as well. This gives you additional equations for derivatives, okay? You solve the system of equations with the original fitting points and with derivatives together. This is still kind of system of equations that you can solve. And then you get spline solution. This is what splines are. You're taking, for example, a quadratic polynomial, which will continue with the same derivative after that point, and same point here. So this polynomial should have same derivatives before and after the point everywhere. Now, this leaves you with these 2 points. Like, what do you do with these 2 points? Because you don't have anything to the left, right? You don't know how it's supposed to be on the left. So you need 2 additional conditions here on the boundary points, because you still don't have enough equations to have single unique solution to that. So there are multiple ways to define that. You can define it in multiple different ways. You can define that this will start at a particular point. You can define that derivative will be 0 here at that point. You can define the derivative at that point will be equal to the derivative at that point, like circular. If it is a repetitive function, it kind of repeats itself. Periodic function, if you know about the functions, this will be periodic. You can define that this derivative will be equal to that derivative after full periods that you are fitting. You can define all kinds of boundary equations which will fit your problem, okay? So there are multiple ways to define spline. There is no like single spline solution to that. You have all kinds of solutions, depends on your problem. And you have standard ways to define these things, and you have less standard things. You still can define in MATLAB or any other coding language for your boundary conditions, all right? So here is just one example for that particular function. So for each pair of points in interval 0, 1, you will get that kind of cubic polynomial, this cubic spline, all right? So that kind of cubic polynomial, then you get that kind of cubic polynomial, and so on. For each interval, you have separate cubic polynomial, and you'll have that system of cubic polynomials which describe all these blue segments between the points. Okay, and total you have 1, 2, 3, 4, 5, 6 of them. Okay, 6 cubic polynomials which are defining that spline in different segments. Any questions on that?
Spline interpolation, you just use the Lagrange polynomial by each
It's not
sector.
Lagrange polynomial anymore. It's just any cubic polynomial in that case.
Then
So you're just finding coefficients of A, B, and C, and D.
how does it find the coefficients?
You're solving system of equations with additional constraints on the derivatives. I mean, I'm not showing the actual solution, but here's how it goes in general, okay? So I can explain, again, waving my hands because the math here is very long when you're writing that explicitly. You can go to any textbook on splines or any description of splines, and it will give you the actual formulas. You have formulas that you actually can use to invert it. So here's how it goes. Let's say you're picking a particular point, okay? And you know that segment I, which is 2 in that case, will be some cubic polynomial. So you need to find AI, BI, CI, and DI, which are coefficients of that polynomial. All right. So one of the equations will be something that we wrote already in Van der Monde matrix. All right. Which will be that when you put in here x3, you should get y3 here. Okay. You're doing the same thing for the S3, right? For that side. Okay. Because this also should be solution of the S3's polynomial. So you'll have two equations here, right? For that single point. One equation is for S2, one equation is for S3. Because they connect at the same point. So they have common point, you have two equations out of it. Now you're also doing derivative of that polynomial, which will be 3 times AI times x squared plus 2 times bi x and so on. You know how to make derivatives of polynomials, okay? So derivative of that thing will be equal to derivative of that thing, which is same thing, but for the next I. So it will be I plus 1 here, okay? So we'll have that additional equation for the first derivative, and then you're computing second derivative of that, and second derivative of that. And you have additional equations. So you have total 4 equations. There's a point, all right? 2 equations are that they have same connection point, and 2 additional equations for derivatives, first derivative and second derivative for each one of them, okay? They are equal, and all of them are linear equations, right? Because these coefficients in degrees are just numbers, and they multiply like 3a, 2b, 1c, it's still linear in ABC, okay? So all of these equations will be system of linear equations, and this system of linear equations will have normal solution by inverting matrices or by some other approaches. But this will have some solution, okay? This is more numerically stable solution in that case. Why? Because you don't need to fit that entire polynomial to multiple points where it becomes kind of unstable, like wiggling. So it's much more difficult to fit to different random points, single polynomials, than to fit to 2 points, family of polynomials. This is just much easier problem, so it's much more stable in terms of computing the coefficients. All right, so you actually can solve it. And Van der Monde matrix for like second, third order, fourth order, it's very close to invertible. Okay, so it's not really having condition number, which is horrible. So you actually can find that type of solutions. Right, so it's numerically stable approach.
But if
Yes.
you have a lot of points, then you have a lot of.
It doesn't matter how many points you have, because you're doing only pairs of points. Right? You have like, you're looking on a single point every time, and you have pairs of polynomials. These polynomials are completely different. They're not the same polynomial. You're not trying to fit polynomial through more points. You're fitting them only through one point together. This is their interfacing point. That's it. So computing a polynomial of low order, low degree, which is interfacing at only one point, which is much easier problem to solve. It's like more computations because you need more polynomials, but the problem itself is much easier. Okay? Much more feasible to have it like very smooth. And all these equations are linear, which is also a nice property to have.
You have the same derivatives throughout all the segments. The only difference would be you'll be like A1, A2.
Only at the edge points. Same derivatives only at these points. Here they could have anything, it doesn't matter. But since this is like order 2 or order 3 typically, they do not change that much, okay? It could look like parabola or like cubic polynomial. So you have like maximum 1 point like that, inflection point or how it's called. So you don't have that kind of behaviors. You cannot have that behaviors because you can have only up to 2 maxima or minima, right? And in this like cubic polynomial, quadratic polynomial will have only maximum 1. Okay, cubic polynomial will have maximum 2. That's not that much. You cannot go up, like maximum it will go up and down. That's it. It will not do something crazy between the points. Right? And especially when it goes already up and down, your derivatives are extremely strong on these ends. And you need that this derivative will fit what happens next. Right? So it's unlikely that you will have oscillation type of thing between the points. Most likely it will be more or less straight line or a little bit curved line, that kind of connection. And that's what typically happens in splines. You don't see much oscillation in it at all. Right?
So for this method, you are always solving the third order.
Typically, yeah. This is most popular one is cubic spline, yes. So third order polynomial is 4 coefficients, yes. Okay, this is the overall algorithm. I already explained that, but to summarize, you have all of these endpoints xi, yi, I equals from 1 to n, and you have to find these polynomials in each pairs, in each interval between the points, all right? That polynomial will be equal to yi at that point, and both of them need to be equal. So this polynomial at xi equals to yi, and the next pi at the next point will be yi plus 1. So it will fit to the second point. So the polynomial should be between the 2 points, okay? So it will fit both of the points. So these are 2 equations that you get. And then you have also for first and second derivatives, you're defining that they need to be continuous, which means they need to fit between the interfacing polynomials. So you have these 2 equations. So in parentheses here, it means derivative, case derivative, and k equals 1 or 2. Okay, first derivative and second derivative of that particular point equals to the next polynomial derivative at the same point, okay, for any point, for every point. And then you have additional boundary conditions. You can specify them as some derivative equals to 0, or that they matching somehow. First derivative has some properties at the boundary condition, at the endpoints, and so on. So it depends. Yes.
I wonder why you just first and second derivatives. Why not use the third one? Third derivative.
You don't need more equations. This is just easier computationally, and you don't need more equations. You have enough equations to fit n parameters with n unknowns. You want n equations for n unknowns. Okay, so each segment will add you practically 4 new variables because you have 4 coefficients to each cubic polynomial, right? So each segment needs to have 4 equations plus adding 4 equations for each segment, all right? And this will give you the exact number of equations that you need. You define smoothness on the derivatives, connection point, this gives you 4 equations. You don't need more. Okay. Example, we want to reconstruct neural spike here. And this is just simulated spike, obviously, some sort of wavy function that we want to interpolate. And we have all of these black dots are computed from that original spike, and the original spike true signal is that black line. Okay. And we're sampling that spike at particular points with equal intervals. So we have black dots and we don't have the black line. But we want to reconstruct the black line using interpolation of some kind. And here you can see examples of linear interpolation, which is practically connecting black dots with straight segments. This is a red line, connecting all of the black dots. And it's okay, it's not great, not connecting very well, but it's fine, okay? So it's kind of, you have a lot of corners here, cutting some corners. All right, this is linear one. You have spline interpolation, which is blue, much better, gets much closer to this kind of interesting corners of the original function, much closer to the blue one. You have other things, Hermite type of polynomials. Also, by the way, very popular thing when you don't have too many oscillations and you have something pretty smooth without oscillations. P-chip is much better. It's other kind of interpolation. In MATLAB, you have many different types of interpolation that you can just use same command, interp1 for one-dimensional functions, interp2 and you have for more dimensions, you can fit surfaces and so on. So here's how you do that. Okay, so this first part is generating that black line. Okay, and we will just use exponent times sine for that purpose. All right, this will be that black line. And then we will have interpolation, and you can use nearest, linear, spline, p-chip. You have many more different kind of interpolations that you can use. So this function is taking a few parameters. first of all, you are saying which points you want to do that interpolation, okay? And these are the points. You're taking that from 0 to 1, okay? Because this is starting at 0 here and gets to 1. This is the range of the numbers that you have for that thing. And the original one was having only 50 points. Okay, now I want 1,000 points in between. You have many points in between, okay? So this 1,000 points, I'm taking the original signal, which is sparse signal, this 50 points. I'm saying what are the values at this 50 points, which are these black dots values. All right, this is a spike sparse. These are, like when you're using nearest, it's just taking the value at this particular points of that function. And then I'm generating define, sorry, for this 1,000 points using that method. Could be linear, spline, or whatever, this cubic spline. And then I'm plotting all of them. So this is just how you plot all of them. These are details, you don't need particular details, but you just plotting all of them, and these are the lines that you get in that plot, right? And these are different kind of interpolations that you have in that function in MATLAB. You have nearest, previous, cheap, Makima, spline, all kind of, okay? Each one of them has particular advantages or disadvantages specifically. You can read about when you want to use them and how you want to use them, but in terms of using that in MATLAB, it's just switching that word. Instead of cheap, you can put here Makima, it will give you something else. Other types of interpolation. So some of them more computationally expensive, some less computationally expensive, but this is the idea. Yes.
One is more common.
Sorry?
Which one is more common to use?
Which one is more common? Linear is the most common, because this is the simplest and computationally least expensive out of all these techniques that you have here, okay? You're just connecting the dots with straight segments. It's simple, it's not overshooting, it's not overestimating different things. It cannot produce you undershoots or overshoots. By definition, it will always be between the points, all right? It's not useful at all for extrapolation in a sense, because it will just continue the previous trend between the previous two lines. Not very interesting, really. So for extrapolation, it's not useful. But for interpolation, it's pretty good for most applications, okay? Unless you want function which looks smooth. You want smooth approximation, interpolation, then linear is not the way to go, okay? Then people typically use cubic, okay? This is the second most popular. But you can show that for many examples, P-chip and Makima are much better approximating the original function compared to cubic interpolation. So it's more computationally expensive, but more accurate. So it depends. If you have like millions of points, you go with probably cubic, and you want it smooth, go with cubic. If you want it very accurate, then go with Makima or P-chip. Yeah, depends on your computational. Right?
Makima.
It looks like a Japanese name to me, so maybe I'm not pronouncing it right. It's Akima cubic. It's modified Akima cubic Hermite interpolation. Okay, so Makima is just name of the parameters in metals. It's actually Akima is the name of the, I guess, inventor of that type of interpolation. Sounds Japanese to me, but I might be wrong about that.
Spacing between the samples make a difference for these, like the Lagrange, or?
Not really. Actually, it's preferred that you'll have even spacing here, but it doesn't have to be. Works without, because look, let's say 2 points are super far away, and you're fitting cubic polynomial to that, so you'll not have any ability to do anything like that, right? But maybe you don't need it in the first place, so it's fine. Okay, but if you do need it and you know that you have a lot of oscillations in your signal and you're just missing some points, you haven't sampled enough, you still want to do something like that, then maybe you need to use some other technique here. Okay, so it depends. Yeah, I don't have any correct answer for that. There is no correct answer. Any other questions?
all these methods are for linear line. You cannot be like somewhere you just empty. All
You have
points.
only dots, you don't have any lines. You are trying to guess what the line is. So you're connecting, this method is what is the line that connects all of these dots and passing through all of them, but behaves nicely between them somehow. And what is nicely depends on your problem. It's smooth nicely, or it's like not overshooting nicely, or it's connecting just in real time. This is nicely for you. It depends on how you define what nicely is. Maybe you need zero order halt if you're using real-time embedded board and you're sampling your signal, and you want to convert it into continuous signal instead of discrete points in real time. So how would you do that if you don't know the future? You just keep whatever was before, or you keep the previous linear extrapolation. These are the methods until you get next point, and then you correct it. Okay. Questions? All right. Thank you.